All right, today we are diving headfirst into one of the most fundamental and, let's be honest, one of the most mind-bending ideas in all of physics, quantum superposition. This is the wild rule that says tiny little particles can be in many places, or in many states, all at the exact same time. So, let's get into it. To really start to wrap our heads around this, let's kick things off with a question. In the world we see every day, things are pretty clear-cut. A light switch is either on or off. When you flip a coin, it's going to be heads or tails. But what if? What if, for the tiniest things in the universe, that word or suddenly became and? Before we can truly appreciate just how strange the quantum rules are, we need a good baseline. We need to understand the rules we live by every single day. In our world, the classical world of things like baseballs and planets, superposition is actually pretty straightforward. Really, it's all about just adding things up. Take waves, for instance. When two waves in a pond meet, their effects combine. They can add up to create a much bigger wave. We call that constructive interference. Or they can do the opposite and completely cancel each other out. That's destructive interference. This is literally how your noise-canceling headphones work. They create a perfect anti-noise wave that superimposes with the sound coming in, and the result? Silence. And it's the exact same idea with forces. If you want to figure out the total force on that blue particle over on the left, all you have to do is calculate the force from each of the other two particles individually. Then you just add them together as vectors, and bam, you've got your final answer. It's simple, it's predictable, it's classical addition. But here's where the story takes a sharp turn. Because when we zoom way, way down to the level of atoms and electrons, that nice predictable world completely vanishes. It's like the universe starts playing by a totally different and frankly a much, much stranger set of rules. Yeah, at these tiny, tiny scales, all of our classical intuition, everything we think we know, it just completely breaks down. So, the first new rule you have to learn is something called quantization. Think about it. You can throw a baseball at any speed you want, giving it a smooth, continuous range of energy, kind of like walking up a ramp. But in the quantum world, energy only comes in these distinct little packets, or quanta. A particle can have this much energy or that much energy, but absolutely nothing in between. It's not a ramp, it's a staircase. And this very idea, this staircase of discrete states, leads us right to the heart of the matter, quantum superposition. And here we're not just adding things up anymore. No, this is about being multiple things all at once. Okay, let's try an analogy to make this a little clearer. Imagine you flip a coin. While it's up there spinning in the air, before it lands, what state is it in?
Now, classically, you just say its state is unknown, right? We just don't know the answer yet. But the quantum view is completely different. It says the particle isn't one or the other. It's actually in a weird mixture of both heads and tails simultaneously. It literally exists in a superposition of all its possible outcomes.
And that is the absolute key to all of this. Quantum superposition means a particle is literally, physically, in all of its possible states at the same time. It's not that we don't know which state it's in. It's that its actual state is that fuzzy blend of all of them. Now, this absolutely bizarre idea is captured perfectly in the famous thought experiment of Schrödinger's cat. You put a cat in a box with a radioactive atom. If the atom decays, a poison is released, and the cat, well, because that atom's decay is a quantum event, it exists in a superposition of both decayed and not decayed. And that means until we open the box to look, the cat is in a superposition of being both alive and dead. This concept was so deeply unsettling that it bothered even the greatest scientific minds. Albert Einstein famously challenged it, asking a friend in a letter, "Do you really believe the moon exists only when I look at it?" That just shows you how profoundly this idea breaks with our everyday experience of reality. So you might be asking, okay, this is a mind-bending concept, it's a cool thought experiment, but why does it actually matter? Well, because this one strange property is the key, the absolute engine behind a world-changing technological revolution, quantum computing. See, your phone, your laptop, they all work using classical bits. A bit is simple. It can be a 0 or a 1. That's it. But a quantum computer uses something called a qubit, and thanks to superposition, a qubit can be a 0, a 1, and a blend of both, all at the same time. This incredible ability to hold multiple values at once is what allows a quantum computer to basically perform a staggering number of calculations simultaneously, giving it the power to solve problems that are flat out impossible for even the biggest supercomputers we have today. But hold on, there's one final crucial piece to this whole puzzle. What happens to this beautiful superposition when we actually try to look at it? What happens when we finally open the box?
So let's put all the big ideas together. A quantum system, like our qubit, exists in a fuzzy superposition of all its possible states. But the moment we measure it, and that just means any interaction with its environment, not just a person looking, that act of measurement forces nature to pick an outcome. The superposition is instantly destroyed in a process we call collapse, and the system is forced into one single definite state. We will only ever find the coin as heads or tails, the cat alive or dead. We never ever get to see the both at the same time state directly.
And that leaves us with the ultimate question, the very one that puzzled Einstein himself. If the simple act of observing the quantum world forces it to change, to pick a single state, what is reality actually like when we aren't looking? That is the profound and beautiful mystery right at the heart of quantum mechanics. Thanks for joining me for this explainer.